Around 13.8 billion years ago, the universe expanded from an initial high density and temperature state. The Big Bang theory explains this. After the initial expansion, the universe started to cool and form giant clouds of primordial elements, mostly hydrogen, with some helium and lithium. These elements were attracted through gravity, forming early stars and galaxies. The solar nebula hypothesis is the standard model for forming the solar system, including the Earth. According to this model, the solar system was developed from a large, rotating cloud of interstellar dust and gases called the solar nebula. The nebula began a contraction that may have been triggered by the shock wave from a nearby supernova. A shock wave would have also made the nebula rotate. As the cloud began to accelerate, its angular momentum, gravity, and inertia flattened it into a protoplanetary disk, perpendicular to its axis of rotation. The center of the nebula, not having much angular momentum, collapsed rapidly, the compression heating it until nuclear fusion of hydrogen into helium began. After more contraction, a T-Tauri star ignited and evolved into the Sun. Meanwhile, in the outer part of the nebula, gravity caused matter to condense around density perturbations and dust particles, and the rest of the protoplanetary disk began separating into rings. Then, successively larger fragments of dust and debris clumped together to form planets in a process known as runaway accretion. Earth started in this manner about 4.54 billion years ago. The proto-Earth grew by accretion until its interior was hot enough to melt the heavy, hydrophile metals. Then, having higher densities than the silicates, these metals sank. This so-called iron catastrophe resulted in separating a primitive mantle and a core only 10 million years after the Earth began to form, producing the layered structure of Earth and setting up the formation of Earth's magnetic field. The giant impact hypothesis for the Moon's formation states that shortly after forming an initial crust, the proto-Earth was impacted by a smaller protoplanet, which ejected part of the mantle and crust into space and created the Moon. The late heavy bombardment or lunar cataclysm began about 4.1 billion years ago and concluded around 3.8 billion years ago. During this interval, a disproportionately large number of asteroids collided with the early terrestrial planets in the inner solar system, including Mercury, Venus, Earth, and Mars. In addition, volcanism was severe due to the immense heat flow and geothermal gradient. Nevertheless, detrital zircon crystals dated to 4.4 billion years ago show evidence of having undergone contact with liquid water, suggesting that the Earth already had oceans or seas at that time. By the beginning of the Archean, the Earth had cooled significantly. Present life forms could not have survived at Earth's surface because the Archean atmosphere lacked oxygen and hence had no ozone layer to block ultraviolet light. Nevertheless, it is believed that primordial life began to evolve by the early Archean, with candidate fossils dating to around 3.5 billion years ago. Some scientists even speculate that life could have started during the early Hadean, as far back as 4.4 billion years, surviving the possible late heavy bombardment period in hydrothermal vents below the Earth's surface. Earth is often described as having three atmospheres. The first atmosphere, captured from the solar nebula, was composed of light elements from the solar nebula, mostly hydrogen and helium. Then, after the impact which created the Moon, the molten Earth released volatile gases. Later, more gases were released by volcanoes, completing a second atmosphere rich in greenhouse gases but poor in oxygen. The new atmosphere probably contained water vapor, carbon dioxide, nitrogen, and smaller amounts of other gases. Finally, the third atmosphere, rich in oxygen, emerged when bacteria began to produce oxygen about 2.8 billion years ago. The first step in the emergence of life may have been chemical reactions that produced many of the simpler organic compounds, including nucleobases and amino acids, which are the building blocks of life. An experiment in 1953 by Stanley Miller and Harold Urey showed that such molecules could form in an atmosphere of water, methane, ammonia, and hydrogen with the aid of sparks to mimic the effect of lightning. Simpler organic molecules combined and formed RNA and DNA, which are the genetic materials that pass from generation to generation. All the details needed to evolve life were stored in that RNA and DNA. Later these genetic materials were covered with other organic compounds like carbohydrates, proteins, and lipids by forming unicellular organisms. Eventually, these unicellular prokaryotic organisms evolved into eukaryotic unicellular microorganisms and multicellular organisms. Organisms that got the ability to convert the sun's energy into food formed the photosynthetic bacteria, algae, and finally, green plants. Other organisms that could not do photosynthesis became consumers and ultimately created the animal kingdom.